Welcome to Coast CCNA Learning, your complete guide to conquering the Cisco Certified Network Associate exam. From the Pacific to the Pines and beyond, all are welcome here. Whether you're just starting your journey in networking or sharpening your skills for the next big opportunity, this series is designed with you in mind. If you're brand new to networking, I suggest starting with the Cisco Networking Academy's Introduction to Networks course. You'll find it right here on my channel. This CCNA series breaks down each of Cisco's official exam topics, from network fundamentals to security basics and automation. Each video is clear, practical, and zeroes in on the concepts and configurations you truly need to pass the exam. In this first video, we're diving into topic 1.1, network components, the fundamental building blocks of any network. Before we explore network components, let's take a quick look at the first 4 layers of the OSI model, because terms like Layer 2 device or Layer 3 device come from here. You're unlikely to see CCNA exam questions directly related to the OSI model, but it's a foundational concept. It describes how data moves through a network organized into 7 layers. Understanding these layers helps with troubleshooting, analyzing traffic, and understanding where different technologies fit. We'll cover all 7 layers in detail later, but for now, let's focus on the first 4. Layer 1, the physical layer. This is where bits are signaled and sent over the network using electrical signals, radio waves, or light pulses. It includes the actual hardware that moves data, like cables, connectors, and interfaces. Layer 2, the data link layer. Here, devices use MAC addresses to move data frames between devices on the same network. Switches and wireless access points operate here, and are examples of Layer 2 devices. Layer 3, the network layer. This layer is all about IP addresses and routing. Devices like routers and Layer 3 switches work here to forward packets between different networks or subnets. Layer 4, the transport layer. This layer ensures reliable delivery using protocols like TCP and UDP, handling error checking, retransmission, and flow control. Together, these layers describe how data travels from your device across the network to its destination, and understanding them helps us identify what each network component does. Let's get into network components, and we're going to start with a fundamental piece of equipment, the router. So, what exactly is a router? What does it do, and why is it so important? A router connects multiple networks together and directs data between them. Think of it as a traffic director for data packets, deciding the best path for information to travel so it reaches its destination efficiently. Let's break that down a little further and see how this all works. When you send an email or stream a video, your data is broken into packets. These packets don't just blindly find their way across the internet. Routers use routing tables to determine the most efficient path for those packets, like GPS directions for your data. Think of routing tables as maps for routers. They help decide where to send each packet based on the destination IP. As the network shifts, these tables must update to keep traffic on the most efficient route. Now, where do routers sit in the grand scheme of the network architecture? Routers operate at the network layer of the OSI model. The network layer is responsible for routing packets between different networks, and IP addresses are the unique identifiers that allow routers to distinguish between these networks. Routers can also perform additional tasks beyond simply forwarding packets. They can provide network address translation to allow multiple devices on your private network to share a single public IP address. They often act as DHCP servers, assigning IP addresses to devices automatically. And many modern routers include firewall capabilities, adding a layer of security to filter traffic. Another key point, routers can learn about other networks dynamically. They do this through routing protocols like BGP, OSPF, or eGRIP. These protocols help routers share information about network topology and adjust to changes, such as a link going down or a new network being added. In short, a router is a critical device that connects networks, routing data based on IP addressing, and supports services essential to modern networking. Let's take a look at a Layer 2 device, the switch. A switch is a device that connects multiple devices within a network, typically a local area network or LAN. Think of it as a central connection point for all your devices within a single area. It forwards data intelligently, helping reduce collisions and improves network efficiency. This intelligent forwarding is key to a switch's performance. A Layer 2 switch operates at the data link layer of the OSI model. This layer is responsible for node-to-node data transfer. It uses MAC addresses, also known as a physical address, to decide where to forward data frames. Key Layer 2 switch features include VLANs, which segment networks for better performance and security, and Spanning Tree Protocol, which prevents loops that can crash a LAN. Layer 3 switches, also known as multi-layer switches, are another common network component in modern networks. They bridge the gap between VLANs and enable inter-VLAN communication. Layer 3 switches offer routing capabilities in addition to switching because they operate at both the data link layer and the network layer. They not only forward frames based on MAC addresses, but can also route packets based on IP addresses, just like a traditional router. This dual functionality makes them versatile network devices. Layer 3 switches are common in enterprise networks, especially at the core or distribution layers where fast routing and segmentation are needed. Their hardware-based forwarding enables low-latency performance in high-traffic environments. And now, you might be asking, we've heard about Layer 2 and Layer 3 devices, what about Layer 1 devices? What role do devices at the physical layer play in network communication? Layer 1 devices don't look at addresses or make decisions. They simply move raw bits across the network. Examples include hubs, which repeat a signal out all ports, and repeaters, which regenerate weak signals over long distances. The next topic deals with next-generation firewalls and intrusion prevention systems, or IPS. First, what's a next-generation firewall? Traditional firewalls control traffic based on IP addresses, ports, and protocols. But modern threats require deeper inspection. A next-generation firewall goes beyond basic filtering. It combines the functions of a traditional firewall with advanced security features, including deep packet inspection, looking inside the content of packets, not just packet headers, application awareness and control, identifying and managing specific apps, like blocking certain social media or file-sharing apps, and often advanced threat protection, like malware detection and sandboxing. So, what about intrusion prevention systems, or IPS? An IPS monitors network traffic for malicious activity and takes action, blocking, dropping, or rejecting dangerous traffic in real time before it reaches its target. In most modern networks, IPS is integrated directly into next-generation firewalls. This means you get firewall services and threat prevention in a single device. However, in some high-security or high-performance environments, you may still find standalone IPS appliances for specialized protection. Together, next-gen firewalls and IPS provide intelligent, layered defense, helping secure modern networks from increasingly sophisticated attacks. Access points are the next exam topic. An access point, or AP, is a networking device that allows wireless devices to connect to a wired network over Wi-Fi. Think of it like a bridge. It connects wireless clients like laptops, smartphones, and tablets to the wired LAN infrastructure. Over the years, wireless networking has exploded in popularity. No longer is Wi-Fi just a convenience. It's a fundamental part of how businesses operate, how people communicate, and how devices connect. This growth is driven by the rise of mobile devices. Laptops, tablets, and smartphones are everywhere. The increasing number of Internet of Things, or IoT, devices, like smart thermostats, security cameras, and industrial sensors, and the need for flexible, scalable networks that can support remote and hybrid work environments. Access points handle all the wireless-specific tasks. They transmit and receive radio signals, manage wireless connections, and ensure devices authenticate and communicate securely. They operate primarily at the data link layer, managing MAC addresses and forwarding data frames between wireless clients and the wired network. But they also involve physical layer functions. The radios and antennas handle the actual transmission of signals over the air. In modern enterprise networks, APs are often managed centrally by wireless LAN controllers, making it easier to configure, monitor, and scale large wireless deployments. Which brings us perfectly to our next topic, controllers. Wireless LAN controllers are devices that centralize the management of multiple wireless access points across a network. Instead of configuring each AP individually, network administrators use wireless LAN controllers to set policies, apply security settings, and manage traffic, all from one place. Today, in addition to traditional on-premises controllers, many organizations are turning to cloud-based wireless controllers. These cloud-managed solutions provide the same centralized control over access points, but with added flexibility. Cloud-based controllers enable administrators to manage wireless networks from anywhere, without the need for physical hardware at every site. This is especially valuable for distributed networks, branch offices, and organizations with a hybrid cloud strategy. Wireless controllers, whether on-premises or cloud-based, help with seamless roaming, allowing wireless clients to move between access points without losing connection, load balancing, optimizing which APs handle traffic to improve performance, efficiently pushing out firmware updates and configuration changes, as well as enhancing security through centralized authentication and intrusion detection. Expanding on network management more broadly, Cisco DNA Center is a powerful platform that works alongside wireless controllers, switches, routers, and access points to provide centralized visibility, automation, and assurance across both wired and wireless networks. It helps administrators design, provision, and monitor the entire infrastructure using advanced analytics and machine learning, simplifying policy enforcement, speeding up troubleshooting, and enabling proactive optimization. While wireless LAN controllers focus specifically on managing wireless access points, DNA Center delivers orchestration and automation for the entire enterprise network, making it easier to maintain performance, security, and scalability in modern enterprise environments. Up to this point, we've been discussing intermediary devices, the middlemen of the network that direct data toward its destination. Now let's shift our focus to end devices, the hosts and clients where information originates or is received. We'll look at how these devices generate, consume, and interact with data across the network. Endpoints are devices at the edge of the network where users, applications, or services connect. This includes client devices like computers, smartphones, tablets, and IoT devices, but also servers, which provide resources and services to other endpoints. Some common examples of endpoints are a user's PCs, laptop, printers, and game consoles. And here's one that might surprise you. Even a smart refrigerator in an office break room can be an endpoint if it's connected to the network. Servers are a specialized type of endpoint that deliver centralized services across the network. They may handle file storage, email, web hosting, database management, or authentication. While primarily serving data to clients, servers can also act as clients when accessing other systems. Whether hosted on physical hardware in a data center or virtualized in the cloud, servers play a critical role in ensuring users and applications have access to the services they need. Understanding servers as endpoints helps clarify their role in the broader network, supporting clients, enabling communication, empowering the services modern organizations depend on. Let's take a closer look at Power over Ethernet, or PoE. Introduced in the early 2000s, this technology has steadily become a critical component of modern networks. It has transformed how we deploy and manage network devices by delivering both power and data over a single cable. At its core, Power over Ethernet allows a single Ethernet cable to carry both data and electrical power to a device. This means you can power network equipment such as IP phones, wireless access points, security cameras, and IoT devices without needing a separate power outlet nearby. Imagine the possibilities. No more scrambling for power sockets or running extra electrical lines. It simplifies everything. In most enterprise networks, PoE power is delivered by PoE-capable switches. These switches act as the power sourcing equipment, or PSE, supplying power directly through the Ethernet cables. The devices receiving the power are called powered devices, or PDs. Think about it this way. The wireless access point your laptop or phone connects to, or the security cameras you walk by in an office or a school, they're almost certainly powered using PoE. This eliminates the need for additional power cords or outlets at those installation points. PoE simplifies deployment, reduces cable clutter, and increases flexibility, especially when installing devices in ceilings, on walls, or in hard-to-reach locations where separate power would be expensive or impractical. As networks grow, PoE-capable switches play a key role in enabling fast, efficient, and scalable deployments across modern enterprise environments. Before we wrap up network components, let's have a look at an example of a question you may see on the CCNA exam from this topic. Practice questions like this one are an important aspect of preparing for the certification exam. We will have practice questions in every CCNA topic video in this course. A network administrator needs to connect 3 separate departments within a building. Each department must be on its own subnet, but all devices must still be able to communicate with one another. Which device would be the best choice to enable this functionality? Let's look at each option. A Layer 2 switch operates at the data link layer. It separates VLAN traffic, but it does not have the ability to route between different VLANs or different subnets, so we can eliminate that choice. A hub is a legacy Layer 1 device. It offers no real intelligence to route between subnets. It simply repeats data out all ports within the same subnet or network. There's no filtering or decision-making involved. We can eliminate that option. A multi-layer switch operates at both layers 2 and 3 and provides routing functions so devices in different subnets can communicate. They are also called Layer 3 switches. They're faster and more efficient than using separate router and switch devices. This is the answer. And we will look at the last option as well. A wireless access point is the device that gets your mobile device onto the Wi-Fi network. It doesn't provide any routing functionality, so we can rule that out as well. Let's wrap up our look at CCNA Topic 1.1 Network Components, the building blocks that make up modern networks. We started with routers, the workhorses of the internet, which connect different networks and forward data between them, making sure traffic takes the most efficient path. They are the gatekeepers of your network, directing traffic to its intended destination. Routers are essential for internet connectivity and inter-network communication. Then we looked at Layer 2 and Layer 3 switches, where Layer 2 switches forward traffic within a local network, and Layer 3 switches add routing capabilities, making them common in enterprise networks and data centers. Layer 3 switches blur the line between switches and routers, offering a hybrid solution for complex network environments. Next, we explored next-generation firewalls and intrusion prevention systems, which help secure the network by inspecting traffic and blocking threats. These security appliances are constantly evolving to combat the ever-increasing sophistication of cyber attacks. They are a critical line of defense for any network. We also covered wireless access points, which provide Wi-Fi connectivity, and controllers, like wireless LAN controllers and Cisco DNA Center, that help manage and automate the network. Wireless networks have become ubiquitous, and these controllers are essential for managing large-scale wireless deployments. They provide centralized control and visibility over the wireless infrastructure. We talked about endpoints, including client devices, servers, and IoT devices, which connect at the network edge and use the services the network provides. These endpoints are the reason the network exists in the first place. They are the devices that users interact with and that generate the data that flows through the network. And finally, we looked at Power over Ethernet, or PoE, which simplifies powering devices like access points and cameras over the same cable that carries data. PoE has revolutionized the deployment of these devices, making it easier and more cost-effective than ever before. All of these components work together in harmony to create networks that are connected, secure, and manageable. Whether for a small business with just a handful of devices or a sprawling large enterprise with thousands of users and devices, the principles remain the same, regardless of the scale. Coming up next, we'll dive into CCNA Topic 1.2, Network Topology Architectures. We'll explore how these components connect together to form reliable, scalable, and flexible network designs, including architectures like campus LANs, data centers, wide area networks, and much more. We'll examine the strengths and weaknesses of different architectures and how to choose the right one for your needs. Don't miss it. Click the subscribe button now so you're ready and notified when the next video drops. And if you found this helpful and informative, please give it a like and share it with others who are also preparing for their CCNA. Your support helps us create more content like this.